right. Good morning, folks. Happy Thursday. I just wanted to let you know that all exams have been graded, so you can find all your information on Canvas. Um, and I did want to remind you folks that tomorrow is the last day to withdraw. So if you're in a situation where you're like, I don't know, this is not going as well as I had hoped, the withdrawal deadline is tomorrow. If you do not withdraw by tomorrow, then you are stuck. You have to take whatever grade you get. So that's how that works. I did send out emails to folks that I was a little bit concerned about, so please check your email in case you are in a situation where your point values that you have so far are a little bit concerning to me, and so definitely make sure to take a look at that. And other than that, I know that a bunch of folks signed up for for meetings this afternoon, so I'm excited to meet with you folks this afternoon. And then if you haven't signed up yet, there are a bunch of times for tomorrow and for Sunday as well, okay? All right, well, with that being said, we're gonna go ahead and get started. So we need to finish up 6.5, okay? We need to finish up 6.5. We've got one more example to go through, so we will go ahead and start working on that, okay? All right, so yesterday, we were able to get a good chunk of this section covered where we were talking about the idea of work. We talked about the difference between maybe formulas that we had seen in the past, this work equals force times distance, and how that was a very special case. But then what we're trying to do is open up that world of what happens if there are non-constant forces, which is much more common than having a constant. And so we took a look at two applications. There are a ton of other applications, but these are the ones we're going to focus on in this class. So we took a look at Hooke's law, which is the application of linear force. So it's not always the constant force applied, but rather there's a spring constant that dictates how much work it's going to take to stretch or compress a spring, okay? And so one important thing to point out, which I think we did actually super well on yesterday, was that the bounds are actually all about the differential. So like how far did you stretch it or how far did you compress it rather than the actual length of the spring. It's all relative to the natural length, okay? So we went through a couple examples on finding that work done. And then at the end of class, we shifted gears towards looking at lifting objects. And with lifting objects, we started with this diagram that kind of looks like what you might get in a textbook. But then we really took some time to break it down and think about where all the parts of that diagram come from. So I hope that conversation was helpful for folks to think about where this formula comes from and why there's the different parts to the formula, okay? At the end of class, we were able to set up our actual integral. So we knew that we had to integrate distance and density and volume, that product. And even though there were a lot of different terms, a lot of the constants we were able to pull out, and we ended up with actually just needing to use the power rule. So 20y squared minus y cubed became 20y cubed over 3 minus y to the 4th over 4. All right, and if you wanted to, for a calculator, you could turn it into a decimal, and if you wanted to leave your final answer as sort of this stage right here, that was also fine, okay? So are there any questions from yesterday? Because I know we talked a lot about concepts, and it's, you know, sometimes hard to kind of internalize all of that. Like, where did these people come up with these formulas from? Okay. Well, if there are no questions right now, then we're going to go ahead and take a look at the last on the last example for this. All right, if you have quiz questions, I'm going to ask you to save that for later. But in terms of example number 4, okay, so we have a different situation where we're lifting objects. So in example 3, we were looking at lifting water out. We're thinking about how do we get water out of a tank. And in this situation, I think it's a little bit more what we tend to think of when we think about lifting objects, okay? So we have a cable that weighs 2 pounds per foot attached to a bucket filled with coal that weighs 800 pounds. The bucket is initially at the top or at the bottom of a 500-foot mine shaft. And so there's space here in between the wording and part A because I wanted us to have some space to draw a diagram, okay? I think that knowing how to draw that diagram is definitely important, but also from this diagram, you can do a lot of pre-thinking to set up parts A, B, and C, okay? So if we think about the situation that we have here, okay, we have sort of this place up here that's like the ground level, and then we have a mine shaft, okay, and so at the bottom of this we have a bucket, okay, we've got a little bucket, and it is attached with a cable to the top so that we can pull this bucket up to the top, okay? Now I'm sure my diagram is not fully accurate, but let's just imagine there's some sort of pulley system and you're pulling this bucket up to the top, okay? So similar to yesterday, it's important that we set up an XY coordinate so we can kind of use that to set up our equations, all right? And so in this case, I'm choosing to have my x-axis down at the bottom, okay? So that I can just sort of count up how far this bucket has gone. And if I choose the bottom as x, then that means that this distance is 500, okay? And as the bucket goes up, we have a greater distance from the bucket to the bottom, and we have a smaller distance from the bucket to the top. If I want to think about the y-axis, the y value, thinking about how much distance is left, okay? Because the distance that is remaining is the part that needs the work. The distance that is already traveled, we don't need to worry about the work there because we already counted it, okay? So at the beginning, the distance is 500. But what happens if the bucket gets up to, let's say, halfway? Okay, so let's imagine that the bucket is now halfway. How much more does it have to go? Like, how much more distance does this bucket have to go?
250.
250, right. And what if we had a bucket that was almost close to the top? Let's say it's traveled 400 feet. How much more distance do we have to raise that bucket?
100.
100, okay. So the pattern that Mariah is correctly identifying here is that the distance that is remaining, we can find that using 500 minus whatever y value it is, okay? So this helps us find the distance remaining to the top of the mine shaft, okay? So the 500 is important because it tells us what's like the worst case scenario. We have 500 feet to go, but as we go, it should get a little easier because we have less distance to travel, okay? So while we're here, let's take a look at the things that are impacting the force of this. And the force impacts the work, right? So the force in this case, and again, some textbooks like the capital F, I like that one. Some textbooks like lowercase f. So either way is fine as long as you know that the expression you're writing talks about the force. What are some things that contribute to the force of this bucket or pulling this bucket up?
2 pounds per foot.
Okay, so that 2 pounds per foot, is that constant the whole time, or does that change as you're pulling the bucket up?
That's constant.
Is it 800 pounds
Okay,
of work?
there's two components here, and I like that you between the two of you, you've mentioned both of them. Okay, so one of the things that we need to consider is the weight of the bucket and the coal. All right, so that weight, that's that 800 that Sean was talking about. Okay, so that's one component of the work. No matter how far the bucket is from the bottom or how close it is to the top, it still weighs 800 pounds. That part doesn't change. But to that, we need to actually consider the weight of the cable, because this cable that is helping us pull it up also increases the weight of whatever it is that we are pulling up. Okay, so this weight of the bucket and the coal, that part is 800. Does that change as the bucket comes up the mine shaft?
No.
No, right? We hope we don't lose any coal, like it doesn't get wobbly, nothing falls out. So this part right here, the weight of the bucket and the coal, okay, this part is actually going to be 800 pounds, and it's going to be 800 the entirety of our situation, okay? Now, Mariah, you are correct in one sense that the 2 pounds per foot, like that cable weighs 2 pounds per foot no matter what, right? That cable, the material that goes into it weighs 2 pounds per foot. That part is constant.
So I have a question about that.
Hold on, can I finish my question?
Yes.
Okay. So my question though is, does the amount of the cable you're pulling change as you go up the mine shaft?
Yes, it does.
Yes. Okay. So when you say that the weight of the cable is constant, that's not quite true. Okay. So it's not quite true because as you pull, you have less cable in the mine shaft. All right. What was your question?
So at first I had said the bucket because I was thinking you added that to the 800 pounds, but then when you read clearly, it's included in the 800 pounds. But
it's the 800 pounds is the bucket and the coal, but it is not the cable.
yes.
Okay. Was that your question?
Yeah, I just didn't know if there's going to be a, like, because in some of the other sciences, you have to account for the weight of the measuring device and, you know, the container and all of that stuff, like in chemistry.
Right. So we have the bucket and the coal. It's already been weighed for us together.
Okay, I just didn't know if there were going to be questions that I'll pay attention to that.
Okay. All right. So the weight of the cable here, we know is 2 pounds per foot, but the amount of cable changes, and it changes according to that distance remaining to the top. So in order to find the weight of the cable, we actually need to take that 2 pounds per foot, and we're going to multiply it by how many feet we still have left to pull it up. And together, that will give you the pounds of weight that the cable is still in the mine shaft. Okay. So before we move on to part A, let's clean this up a little bit. So I've got 800 from the bucket and the coal, plus 1,000 because I distribute that 2 in the 500, and then minus 2y. Okay, which I can further combine to make 1,800 minus 2y. And this represents the force function for the situation where we are pulling this bucket up the mine shaft. Okay. I think you'll find in general that in our applications, we're not going as detailed as you might find in your science classes. So please use what examples we're going through and are on the quiz as sort of a reflection of what you should expect. Okay, that those expectations have not changed, the alignment between the quizzes and the exam. All right, so part A here, it says determine the amount of work required to lift the bucket to the midpoint of the shaft. All right, so if we set up our work function, we know that work is the integral of the force function over whatever distance we're doing. And I suppose we should actually call this f of y, since we're aligning it with a vertical system. And so let's set up our integral. I know I need to integrate the 1,800 minus 2y dy, okay? I've seen a few people recently, I don't know what's happening with this, maybe it's just midterm blues, but like mixing their x's and y's in the integral. So just make sure that you have everything with the same variable all the way through, because when you mix and match, that's kind of a sign that you're not really clear on what's going on, okay? So make sure your variables match, make sure you have the notation there. What are our bounds for this? If we are thinking about how much work required to lift the bucket from the bottom to the midpoint.
0 to
500.
I'll take the 0. What was the second one?
250.
Yeah, we're only going to go up to 250, okay? So while we might not be as picky as some of the science problems, we still want to make sure we have the right bounds, right? That's what we're focusing on, is that we've got our setup correct, and then we can compute it from there, okay? So another common mistake that I've seen recently from some folks is that folks are just like, they're like, here's the integral, okay, so now I just plug in my bounds. All right, that too is kind of an indicator that you're not really engaged with the problem, because you can't just take the integral symbol away. You actually have to integrate what you have before you plug in the bounds, okay? So let's change this. We don't want 1,800, we want 1,800y. And we don't want 2y, we have, that came from y squared, okay? And if you put this into the calculator, you should end up with 387/500 foot-pounds. Okay. Any questions about part A so far?
Why would we set the bounds to 250 instead of 500?
Because we're going to the midpoint.
Oh, okay.
We're only going halfway up, all right?
Gotcha. Thank you.
All right, but that question kind of leads into the next two parts, all right? So the only thing that changes between parts A, B, and C are the bounds, because the function is still the same. Our force function is still the same. We're still going to have 1,800 minus 2y, because that represents the bucket and the cable as it goes up the mine shaft, okay? So I'll give you a moment to think about what those bounds might change to for part B and part C, okay? So take a moment, think about what those bounds might be. And then let's share out what values we think we have and why we have them. All right. Anyone have ideas for the bounds for part B?
500 to, or 250 to 500.
250 to 500. I love that. 250 to 500. Now, do we think it's going to be more work or less work for the second half than the first half?
Less,
Less. Why?
because of the weight of the rope.
Yeah, exactly, right? There's less cable, so there's less work. And so if we do the same thing here, we're going to integrate and we're going to plug in these bounds. And even though these bounds are bigger numbers, we end up with a smaller number, which means that Mariah's intuition was correct, that we are looking to have less work in that second half because we've done that, the bigger part of the work where we had more cable, everything was heavier. And so it took more work in the first half, okay? What about the bounds for part C?
500.
Yep, great job. And Broy, thank you for that. So we're going from 0 to 500, okay? Now I could integrate this again, or I could take my answers from part 1 and part 2 and just add them together, right? Because the work from the first half, so if we call this W sub 1 and W sub 2, if we add them together, it should give us the total work that we have. And so we have this much work over 500,000 foot-pounds to lift this bucket from the bottom all the way to the top, okay? So that wraps up section 6.5 in terms of work. So we've got springs, we've got lifting objects, whether that be like example 4 where we're literally lifting an object, or example 3 where we're kind of pumping a liquid out of a certain container, okay? But all of them go back to the same idea that if we integrate force, we will get the work. All right, any questions before we move on about the lesson part right here, not about quiz questions? We can do those at the end. Okay. All right, so I'm going to stop this share. I'm going to